Welcome back to Arxflix. Today, we're diving into a new paper titled Medusa, Simple LLM Inference Acceleration Framework with Multiple Decoding Heads. This research tackles the challenge of speeding up inference in large language models, LLMs, by introducing a novel method that leverages parallel decoding. Here's a visual representation of Medusa. It adds extra decoding heads to the LLM, allowing it to predict multiple tokens simultaneously. These heads are trained in a parameter-efficient way, ensuring seamless integration into existing models. Let's break down the key components of Medusa. LLMs are memory-bound, meaning their inference speed is limited by the memory bandwidth of accelerators. This bottleneck arises from the sequential nature of autoregressive decoding, where each step generates only one token. Speculative decoding, a popular approach to address this, uses a smaller draft model to generate candidate tokens. However, finding and integrating a suitable draft model can be challenging. Medusa offers a simpler solution by adding decoding heads directly to the original LLM. These heads are trained efficiently and don't require a separate draft model. Medusa introduces two key components: Medusa heads and tree attention. Instead of using a separate draft model, Medusa adds decoding heads to the last hidden states of the original LLM. These heads are trained alongside the original model, ensuring alignment in their probability distributions. This equation defines the kth Medusa head, where ht represents the last hidden state, and w1, k, and w2, k, are the weights of the feed-forward network. Medusa heads generate multiple candidate continuations, which are processed concurrently using tree attention. This mechanism allows for parallel processing of candidates, enhancing the efficiency of decoding. Here's an illustration of tree attention. Each branch of the tree represents a candidate continuation, and the attention mask ensures that each token only attends to its predecessors. Medusa offers two training strategies, Medusa 1 and Medusa 2. Medusa 1 trains the Medusa heads with a frozen backbone model. This approach is simple and requires minimal computational resources. The total loss for Medusa 1 is a weighted sum of the losses for each head, where lambda chi balances the contributions of different heads. Medusa 2 jointly trains the Medusa heads and the backbone model. This approach allows for further optimization of the Medusa heads, leading to greater speedup. The total loss for Medusa 2 includes the loss of the backbone model, math call textum, in addition to the Medusa heads losses. Medusa also introduces extensions to handle situations where no training data is available and to improve the efficiency of decoding. Instead of using rejection sampling, Medusa proposes a typical acceptance scheme to select plausible candidates. This approach uses the prediction probability from the original model to determine acceptance. This equation defines the typical acceptance criterion, where epsilon and delta are hyperparameters. When no training data is available, Medusa employs self-distillation to generate a training dataset from the model itself. This approach ensures that the training data aligns with the model's output distribution. Medusa allows for the construction of sparse tree structures to optimize the efficiency of decoding. This approach leverages the accuracy of different top predictions from the Medusa heads to build a more efficient tree. The paper presents experiments on models of varying sizes and training methods, demonstrating the effectiveness of Medusa. Medusa 1 achieves a speedup of 2.18x on Vicuna 7b and 2.33x on Vicuna 13b. Medusa 2 further improves the speedup to 2.83x on both models. Self-distillation is shown to be effective for models where training data is not available, with Medusa 2 achieving a speedup of 2.3x on Vicuna 33b and 2.6x on Zephyr 7b. Medusa is a simple yet effective method for accelerating LLM inference. It offers significant speedups without compromising model performance, making it a promising approach for improving the efficiency of LLMs. Thank you for watching. Don't forget to like, subscribe, and share this video with your fellow researchers. And be sure to check out the paper for more details. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.